Okay. Bottom of the screen it says introduction. But Mina, what are we getting introduced to? I'll give you an answer. We're getting introduced to the nature of light, except we're skipping ahead to the theory of special relativity. What is the theory of special relativity, you ask? Well, we've got to answer this question. How does the behavior of light affect components of time, space, and matter? In order to address this question holistically, we have to follow along with these topics, which essentially our inquiry question is comprised of. So we have to deal with length contraction and time dilation. We have to deal with Einstein's first and second postulates and what they go over in detail. We have to go over Maxwell's equations briefly because doing them in detail would be far too strenuous. They have a lot to do with the speed of light. We also deal with the photon in a box example. What happens if I'm traveling in a rocket of velocity a, perpendicular to a photon traveling at the speed of light in a box of fixed height h? It's perpendicular to me. What happens then if I travel in a different rocket at velocity b, where velocity b may be greater than velocity a? We'll go over what happens then. We'll also go over why space and time don't really exist. Why don't they exist? Do you exist? Do I exist? What's constant can we rely on and depend on to be universal truths? No matter what frame of reference you're in, what's constant? Well, we can answer that. What is constant? Well, we're going to say the speed of light and space-time. How do we deal with relativistic momentum as well? And the equation for relativistic momentum will be discussed in further detail as well. We're also going to say why nothing can really reach the speed of light. If you reach the speed of light and you were surrounded by light, what you would see is the electric and magnetic waves separating. Why can't this happen? Why can't you reach and observe things from the speed of light? Well, we're going to discuss that. We're going to say that it denies Maxwell's third and fourth equations, by the way, because Maxwell's third and fourth equations, when observed in tandem simultaneously as things happen in the universe, every law is operating simultaneously. The third and fourth equations together state that an electromagnetic field or a wave will have oscillating electric and magnetic fields within it. And if you traveled at the speed of light and observed the stillness and separation of an electric and magnetic wave, you would see that you're breaking Maxwell's third and fourth equations. So you can't really reach the speed of light. We're going to go into more detail as to why you can't reach the speed of light later on as well. We're also going to go over the mass-energy equivalence. You've seen it, you've heard it, non-stop, everywhere. When you're a kid, you don't know what it means. When you grow up, you don't know what it means. If you still don't know what it means, we're going to go over that as well. We're going to say E equals mc squared. Energy equals mass times the speed of light squared. The speed of light is already a huge number. Something near 3 times 10 to the 8th power. We're going to say, okay, if we square that number, which is an even ridiculously larger number, we're going to multiply that by our mass, and we have an incredible value because that's the amount of energy within the total mass of the system. And it's an immense amount of energy. How does this energy not get released spontaneously? How do things hold together? How do things not just blow up on us? Well, we're going to answer that, aren't we? We're also going to say why light can travel in a vacuum. Well, the propulsion from propagation due to Maxwell's third and fourth equations, we see that there's a strengthening and weakening simultaneous, oscillating effect between the two components or constituents of an electromagnetic field. How they cooperate and propel each other, the strengthening of electric wave produces a magnetic field, and then the magnetic field strengthening produces an electric field, and they oscillate and alternate. It propagates, it progresses. It doesn't need, electromagnetic waves do not need a medium through which to travel. Now, we're also going to talk about the production of energy by the sun as an example of our mass-energy equivalence. Well, we're going to look at different types of energy. We're going to look at, different wavelengths of the electromagnetic spectrum that are released by the sun. We have ultraviolet, we have visible spectrum, we have all of these things. We have photons, which are massless. We're going to go over things like the production of energy by the sun, the matter and antimatter interactions. We're going to go over the different proportions of energy released in different ways through the different types of mass energy equivalences we can get, the different examples. So with the sun, we have the matter and antimatter interaction. Matter plus antimatter equals boom. Alright? And the example we go through with that is a positron and an electron coming together. What type of energy is released? How do we get this energy, calculate this energy? Well, we can luckily calculate it with E equals mc squared. We also go over the combustion of fuel, conventional fuels, liquid fuels. How do we power ourselves, our day-to-day life, our world, our industry? What are the uses and applications of all these scientific concepts? This entire whiteboard full of all these things of light and light and energy and relativity. How do all of these convert to applications? How are they useful to me and you in day-to-day life, in industry, in jobs? How useful are these principles when applied? We're going to talk about that. Don't you worry, because we're going to go over all of it. It's all happening. We also have our equations here. Relativistic momentum. Right? We have our mass energy equivalence, which is so easy. It rolls off the tongue because it's so ever so popular. E equals mc squared. Don't even need to write that down, to be honest. We have our 4 equations from Maxwell in their differential form, because there's a differential and an integral form. When you refer to Maxwell's equations, you are referring by default to the differential equations generally. So you have all of these principles, these mathematical equations, these physical concepts, and they come together. How beautiful is this harmony that all of this maths, all of the theoretical physics behind it, and the observable, both macro and micro. We have our observable in day-to-day life, which is very rare when it comes to relativity. You can't get an accurate image of the universe without factoring in relativity, without factoring in time and length, how they change and warp because of the speeds you travel at, how mass interacts with things. How does mass equate to energy? You need these questions answered if you're really going to go out into the world and do the work that needs to be done. It's going to be a series of videos. The sequence of the videos on the website, the videos are going to be attached to the relevant page of writing. They will not be in the sequence presented here in the introduction. They will be in a more logical order. And so I hope you enjoy this lecture series.